Hello students, in this video we are going to perform the second exercise problem. Okay, so let us consider an open loop system having a DC gain of A0. Okay, so this is the DC gain, and it also has two poles, one at 10 megahertz, the other one is at 500 megahertz. Okay, now using this open loop system having two poles, let us try to build a unity gain feedback, which means that we have a beta factor that is equal to 1, right? Yeah. So let us try to compute what is the DC gain of this open loop system for phase margin of 60 degree. Now we know from the definition of phase margin, the phase margin could be expressed as 180 degree plus the phase angle of the loop gain evaluated at omega equals to omega gx. Now again, what is this omega gx? Omega gx is a frequency at which the loop gain magnitude evaluated at omega equals to omega gx is basically equal to 1. Correct? Yeah. So first, let me derive some kind of idea based on the open loop system. Here, I have tried to plot the open loop magnitude versus the frequency. Okay. Now let us have somewhere the gain A0, because since we don't know the magnitude of A0, let us assume that it has some kind of graph. Okay, and the moment we reach the first pole, then we know that the gain degrades at a rate of minus 20 dB per decade, and the moment it reaches the second pole, we know that there will be a further decay of minus 40 dB per decade, right? So this is minus 20 dB per decade, and this would be at a rate of 40 dB per decade. So this is one of the possibility, correct? And the next possibility is something like this. I can have the same kind of graph, right? And the moment I reach the first pole, I can have the gain getting degraded, and it touches this omega p2, okay? And after then the graph would further step down at minus 40 dB per decade. So this is one of the other possibility that I have. So what could be the third possibility? The third possibility is something like this. So I have a gain again of same magnitude, but the point is, after this omega p1, the graph would have stepped down, and we would have reached a gain at omega equals to omega p2 that might be in the negative scale, right? So after then, I would have a decay of minus 40 dB per decade, and this would be falling at a rate of minus 20 dB per decade. Now the question here is, which out of these graphs are valid? Okay, so in order to talk about this, what I really need is the phase margin information. But phase margin is a kind of parameter that is basically related to the loop gain and not to the open loop system, right? So let us try to extract the loop gain information based on the information that is given in the question. Now what is given here is the beta that is equal to 1. So how do I plot the closed loop transfer function here? What we know is the closed loop could be expressed as something like 20 log of 10 1 upon beta, and since the value of beta is equals to 1, this ratio is basically a 1. So what would be the value of 20 log of 1, which is nothing but a 0 dB. So I have a kind of closed loop hanging around this 0 dB line, and when it intersects this particular scale, and this is where I have my omega gx, correct? And for the second case, I draw the same line at 0 dB for my closed loop gain, because since the value of beta is basically equal to 1, okay, so we end up with the same kind of graph. But this time our omega gx would end up at a frequency that is equal to omega p2. Okay, and the third possible condition could be having a line something like this, and the intersection between the open loop and the closed loop would end up having a frequency defined as omega gx, right? Yeah, after then the graph would follow some open loop transfer graph. Now how to evaluate the loop gain? So the loop gain is nothing but it's the difference between the open loop and this closed loop. So whichever the things that I'm shading, it's all representing the loop gain for different cases, but we don't know which among these three shaded graphs are valid for our loop gain expression, correct? From phase margin, one would get the value of phase angle at omega equals to omega gx, right? So I can write the phase value for a phase margin of 60 degree, one would end up with 120 degree, correct? So what we know is, if a value of omega gx falls after this omega p2, we'll have obviously the phase value of this particular graph having more than 135 degree, in a way that at omega equals to omega p1, one would end up having a phase value that is equal to 45 degree, right? And after then, when we go for a value of omega that is a decade away from omega p1, that is 10 times that of omega p1 frequency, it's obvious that this pole might have introduced a minus 90 degree phase, correct? And the moment we are trying to approach to a frequency that is a decade before this omega p2, so which means that when we are around 0.1 times that of omega p2 value, okay, we will have the same 90 degree. And after then, the moment we reach this omega p2, one would have a phase which would be equal to minus 135 degree, right? So if at all, if I try to draw a graph something like this, one would end up having a kind of graph something like this, and it moves on, and then again a graph, correct? And then each of the pole would introduce a maximum of 90 degree. So since we have two poles in our system, it adds up to 180 degree, right? And this is how the plot would look. Now in this case, if I have a omega gx after this omega p2, then what is the phase value one would end up? A phase value that might be greater than this minus 135 degree. So it means that whatever we drawn as a first condition is not valid one, right? Because what we wanted is, we want to have a phase value as minus 120 degree. Now let us go for the second case. So with a similar argument, the phase value one would end up having omega gx equals to omega p2. We know that we would end up having 135 degree. So again, this will not satisfy the phase angle that is required, correct? The only possible way of having this omega gx is somewhere between this omega p1 and omega p2, correct? So this is a kind of a broader intuition, like where exactly our omega gx would lie for a given phase margin. Now let us get into this problem. What we know is, the phase in general could be written as something like minus tan inverse of omega divided by omega p1, okay? And this is the phase that is introduced by this omega p1 pole, and the second pole introduces this amount of phase, right? And that could be expressed as something like minus tan inverse of omega divided by omega p2. Now we know what is the value of omega p1, we know what is the value of omega p2, and we also know what is the phase phi at omega equals to omega gx, okay? So which is nothing but 120 degree, and that's supposed to be equal to tan inverse of omega right now becomes omega gx, in the place of omega as omega gx, divided by 10 mega radians per second, or whatever the notion that you want, okay? It's just the ratio, minus the tan inverse of omega gx divided by 500 mega. Okay, so I need to convert these values in terms of radians, so I just multiply with 2 pi, and this also with 2 pi, so that the omega gx will be in terms of radians. Okay, now how to express this 2 tan inverse term? So what we know is, if we have something like tan inverse of x plus tan inverse of y, then this expression could be rewritten as tan inverse of x plus y divided by 1 minus xy. Now substituting our expression in the place of x, which is nothing but omega gx divided by this 2 pi 10 mega, okay, and again tan inverse of omega gx divided by 2 pi 500 mega, okay, and that's supposed to be equal to minus 120 degree. So you can just cancel out all of these negative terms, and you can rewrite this entire expression based on this, correct? So it would be equal to omega gx divided by 2 pi 10 mega plus omega gx divided by 2 pi 500 mega divided by 1 minus omega gx square into this product term, which is 2 pi 10 mega into 2 pi 500 mega. Okay, yeah, so that's supposed to be equal to tan of 120 degree. Okay, so once you do all this arithmetic, you will get a kind of polynomial which is of second order, right? So the final expression that one would end up is having a value of omega gx that is equal to this value. Okay, yeah, so now that we computed the value of this omega gx, okay, yeah, so from this graph still we yet to have to compute the value of a naught. So we know from our basic geometry, I know the value of this point, right? So what is this point? Basically I have some x value and a y value. So let us assume that I have y2 comma x2. So basically I can mark this particular point with this set of terms, right? Similarly, this particular intersect could be represented as a set of two terms, right? Which is nothing but y1 comma x1. Now what is the value of y1 that we have here? The y1 is nothing but the 0 dB. So this is in terms of 0 dB. And what is the value of x1? Is nothing but our omega gx. So we know both the values of this particular point, whereas the other end of the point, what we know is the x2 value that is equal to 10 megahertz. Okay, but what is unknown is our y2, which is nothing but that is equal to 20 log of a naught, correct? So now these two points are basically connected by a straight line, okay, which is having a slope of minus 20 dB per decade. So we know from the basic math that this could be expressed as a kind of line equation, right? So this is nothing but y2 minus y1, where the y1 value is basically a 0 dB and the slope is nothing but minus 20 dB per decade, and x2 minus x1, right? So the value of x2 is basically our omega p1. Okay, now since this particular scale is plotted in terms of log, so I forgot to write that. So this is in terms of logarithmic scale. So since we have a value of x1 that is equal to log of omega p1, and this is our x2 value, minus, so what is the value of our x1 here? The x1 is having a value that is equal to log of omega gx. So this difference, since they are in terms of logarithmic scale, you would end up with a kind of ratio of log of 10. Sorry, so whatever I've written has gone, but anyhow, nevertheless, so the difference between the x2 and x1, since they were in terms of log scale, could be expressed as a kind of ratio like this. So since we know what is the value of this omega p1 and our omega gx, so this is the answer for this particular exercise.